Hello and welcome to lecture number 12. So far we have been discussing on central forces. So this lecture is a continuation on central forces, and in today's lecture we'll be discussing more on some fundamental properties of central orbit. So what we have done so far is we have considered inverse law force field, which is given by f of r equals to negative k over r squared. So this is a central force, and because it is a central force, it is conservative in nature, and then we can immediately say that the force is given by the negative gradient of the potential function v. So we have negative dv over dr. So from here we can also find out the value of the potential function as a function of r. So this will be negative k over r. Now what we do, and if we make the substitution that r equals to 1 over u, then we can rewrite this equation in terms of u as a function of u. So we have f of u equals to negative k u squared, and v of u will be negative k times u. So using this force and the potential, what we have done is we found an equation for the orbit. So we had r of theta, which was given by L, the semi-lattice rectum, divided by 1 plus epsilon times cosine of theta minus theta naught. So in terms of the variable u, this will be simply u of theta. So that's the reciprocal of r. So this will be 1 over L times 1 plus epsilon. So what we're going to do, we are going to consider simply cosine of theta. Here we have assumed that the axis is at theta equals to theta naught. So this is the equation of the orbit. Now we have the parameters defined as dl, which is given by the angular momentum squared, L squared, divided by mass times some constant of proportionality k, and we have the eccentricity given by a L squared divided by m times k. Now here this constant a is an undetermined term. That means our task will be to remove this particular undetermined term so that we can bring epsilon in terms of the known variable. So let's do that. Our task will be to write epsilon in terms of all the known variables. In order to find the value of this eccentricity, we will begin by considering the total energy of the system, which is a conserved quantity. So we have the energy given by the sum of the kinetic energy and the potential energy, and when we consider this as a constant quantity, then we had a second form of a differential equation, which was given by du over d theta whole squared plus u squared. So this is equals to 2m over L squared multiplied to E minus V. Right, and this V will be a function of u. Fine. Now since we considered the equation of the orbit, which is u of theta as 1 over L times 1 plus epsilon cosine of theta. So from here, if we differentiate both sides with respect to theta, then we have du over d theta. So that will be equals to negative epsilon sine theta divided by L. So let's substitute this into our differential equation, and we know v of u as well. Let's write it down. V of u is negative k times u. So our differential equation now becomes negative epsilon over L sine theta whole squared plus u squared. So this is u squared. That will be simply 1 over L squared multiplied to 1 plus epsilon cosine theta whole squared, which is equals to we have 2m over L squared multiplied to the energy E minus of negative ku. So we'll have a positive k times u, and u will be replaced with k over L times 1 plus epsilon cosine theta. So let's simplify this particular equation. So we'll have epsilon squared divided by L squared times sine squared theta, plus we have 1 over L squared. So that's multiplied to 1 plus epsilon cosine theta whole squared, which is simply 1 plus 2 epsilon cosine theta plus epsilon squared cosine squared theta equals to 2m over L squared times E plus K over L plus K epsilon divided by L times cosine theta. Fine. Now what we're going to do is we are going to multiply throughout with L squared. So we'll take L squared and multiply throughout with it. So this will get multiplied to L squared. And this is going to give us epsilon squared sine squared theta plus 1 plus 2 epsilon cosine theta plus epsilon squared cosine squared theta. And this value is equals to, so we have 2m over L squared times L squared. We have E plus K over L plus K epsilon over L times cosine theta. Now this epsilon squared sine squared theta plus epsilon squared cosine squared theta, they will get combined to become epsilon squared. So we have epsilon squared plus 1 plus 2 epsilon cosine theta, and that's equals to 2m over L squared. Now recall that we defined the parameter L as L squared over mk. So we will substitute L in all the terms that has L on the right hand side. So we will get 2m over L squared. So we had small l squared, so that will be L raised to the power of 4 divided by m squared k squared multiplied to E plus we have k over L, so that will be k times m k squared divided by L squared. Coming to the third term, we have k, so divided by L, so L will be L squared over mk, so that means we get m times k squared, and we have epsilon, so epsilon can be also replaced with, we have epsilon defined as a L squared over m times k, so that will be a L squared divided by m times k times cosine theta. So we'll see that there will be a few terms that will get cancelled out. So we have one L squared cancelling out, so this will become L squared. Then we have one m cancelling out, so that leaves us with one single m. Then we have L squared, m, and one k cancelling out. So that means we will get epsilon squared plus 1 plus 2 epsilon cosine theta. So here we have 2l squared over mk squared multiplied to E plus m times k squared over L squared plus, so here we are left with a single a times k, so we have cosine theta. Fine. So let's multiply 2l squared over mk squared. That gives us 2l squared over mk squared times E plus, so the second term will be left with only 2 plus we have 2l squared a divided by m times k cosine theta, and on the left hand side we have epsilon squared, so epsilon will replace with this particular value, so that will be a squared L raised to the power of 4 divided by m squared k squared plus 1 plus 2 times epsilon. So 2 times epsilon is a L squared over mk times cosine theta. So here we can see that this particular term gets cancelled out from both sides. So we should get a squared L raised to the power of 4 divided by m squared k squared. Let's keep this on the left hand side. We'll take this one to the right hand side. So we have 2L squared E divided by mk squared plus 1. Then we're going to multiply throughout with m squared k squared. So multiplying throughout with m squared k squared. So we'll see that this term and this term gets cancelled. So on the left hand side we have a squared L raised to the power of 4 equals to, so here m squared m, so that means 2L squared E times m plus m squared k squared. Fine. Now we'll divide both sides with L4. So we have a squared E equals to 2em over L squared plus m squared k squared divided by L raised to the power of 4. So a squared will be, so let's take the second term as the common factor. So we have m squared k squared divided by L raised to the power of 4. So that will give us 1 plus, we have 2em over L squared, that's multiplied to L raised to the power of 4 divided by m squared k squared. So we have a squared equals to mk divided by L squared whole squared 1 plus, so 1 of the m gets cancelled, L squared, this will give us L squared. So we have 2L squared divided by m k squared, and we know that our value L is equals to L squared over mk. So that means here we have a squared is equals to 1 over L squared. So this is 1 plus 2L squared divided by mk squared. Fine. And we can do one more adjustment here. We know that epsilon is equals to AL squared divided by mk. So in place of L squared divided by mk, we'll replace it with L, so that we have epsilon is equals to A times L, or we can say, so if we cross multiply both of them, so we have AL whole squared, so that's equals to 1 plus 2EL squared over mk squared. So this is epsilon squared. And finally, to get the value in terms of epsilon, the eccentricity, we'll take the square root. So we have 1 plus 2EL squared divided by mk squared. This is an expression for the eccentricity, meaning it gives the eccentricity of an object which under the action of a central force or the inverse square of force is moving in an elliptical path. Now that we have obtained the expression for the eccentricity, what we'll try to do next is try to find out an expression for the velocity. So we'll begin with the differential equation. So we have du over d theta whole squared plus u squared equals to 2m over L squared multiplied to E minus V. Now we know that the total energy of the system is given by the sum of its kinetic energy and the potential energy. So that means E minus V. So that will be equals to the kinetic energy, and the kinetic energy will be given by half multiplied to the mass of the object times the velocity squared. So we'll use this value. So that means we have du over d theta whole squared plus u squared equals to 2m over L squared multiplied to half mv squared. So here the 2 and 2 gets cancelled out, and if we write this equation in terms of v squared, so we will have L squared over m squared multiplied to du over d theta whole squared plus u squared. So this is the expression for velocity, and this is going to be a generalized expression. So let's write it down. This is a general expression which means that this is expression holds for velocity of any kind of a central orbit. So in our particular case, we use the inverse square law. So we will study that case in a moment. What I'm trying to say here, that this particular equation for the velocity can be used to determine the velocity for any kind of a central orbit. So let's come to our specific case. So what we have done, we're talking about the inverse square law. So for our inverse square law, what we have is f of u equals to negative ku, and here we have considered the equation of the orbit, which is u of theta is given by 1 over L times 1 plus epsilon cosine of theta. Here again we have considered theta 0, that's equals to 0. Fine. Now what we'll do, we'll try to find an expression for the velocity for this inverse square law motion, that means for that particular part. So what we will do, we will begin by first taking the derivative of u with respect to theta. So this is going to give us negative epsilon over L sine theta. Since we need du over theta whole squared, so let's square it here. So we have du over d theta whole squared. So that will be equals to epsilon squared over L squared times sine squared theta. Fine. Then we also need a u squared term, so we'll square this. So we'll have u squared equals to 1 over L squared 1 plus epsilon cosine theta whole squared. So that's an identity. So we have 2 epsilon cosine of theta plus epsilon squared cosine squared theta, which is 1 over L squared plus 2 epsilon over L squared cosine of theta plus epsilon squared L squared times cosine squared theta. So we'll add these two terms. So we'll add du over d theta whole squared plus u squared and divide it with L squared over m squared, and this will give us an expression for v squared. So let's do that. Where v squared equals to L squared divided by m squared. So we have epsilon squared L squared sine squared theta added to 1 over L squared plus 2 epsilon over L squared cosine theta plus epsilon squared L squared cosine squared theta. And we can immediately say that 1 of L squared is a common factor in all the 4 terms, so we can pull that out. So we have the momentum squared divided by m squared times L squared. Here we have epsilon squared sine squared theta, the first term, and if we look at the 4th term, we have epsilon squared cosine squared theta. If we take epsilon squared as the common factor, so that will be multiplied to sine squared theta plus cosine squared theta, which is the identity with a value of 1. So plus we have 1 over L squared, since we have already taken 1 over L squared as the common factor, so we have 1. And for the 3rd term we have 2 epsilon cosine theta. So this is the expression for the velocity of the particle which is under the influence of an inverse square law force. So what we'll try to do next is we'll try to solve a problem based on this particular equation of velocity. We will try to determine the expression for a velocity at random points on the path, which can be either an elliptical path or a parabolic path. In this particular problem, we have an attractive inverse square force field, and this is given by this particular expression. Now we need to show that the velocity at any point along the path, so it could be either a parabolic path or an elliptical path, it might be given by this 2 expression. If it's a parabolic path, it will be 2k over L times cosine of theta over 2. And if it is an elliptical path, we have to show that the velocity is given by this particular expression. So let us begin. So what we'll do, we'll begin by first noting down the expression for velocity that we obtained. So v squared was found out to be equals to L squared divided by m squared times L squared. We have 1 plus epsilon squared plus 2 epsilon cosine theta. Now for a parabolic path, we know that for a parabola, let's write it down, the epsilon value is equals to exactly 1. So we'll substitute it here. So we'll have L squared divided by m squared times L squared. So we have 1 plus 1 squared plus 2 times 1 times cosine theta. So that gives us L squared divided by M squared times L squared. We have 2 plus 2 cosine theta. So we can pull out the 2 from both the two terms. So this will be equals to 2L squared divided by M squared L squared times 1 plus cosine theta. Now we are going to use the identity that cosine of theta, this is the half angle formula. So that's equals to 2 times cosine squared theta over 2 minus 1. So that means 1 plus cosine of theta. 1 plus cosine of theta. So that will be equals to 2 times cosine squared theta over 2. So we'll substitute that in place of 1 plus cosine theta. So that means our expression for velocity will now become v squared equals to 2 times L squared divided by M squared times L squared. So this will become 2 times cosine squared theta over 2. Fine. Now what we'll do in the next step, we are going to substitute the value of L with, we know that L is defined as L squared divided by M times K. So L squared will be, squaring both sides gives us L raised to the power of 4 divided by M squared K squared. So let's substitute it here. So this 2 and 2 gets multiplied to give us 4 times L squared whole divided by M squared times, so in place of L squared we'll have L raised to the power of 4 divided by M squared K squared times cosine squared theta over 2. You can see that M squared gets cancelled out, and that 1 L square from the numerator and 1 L square from the denominator will cancel out. So this is going to give us the expression of velocity v squared as 4 times K squared divided by L squared times cosine squared theta over 2. And if we take the square root on both sides, and we'll consider the positive square root only because velocity is a positive quantity here. So we'll have 2k divided by L times cosine of theta over 2. So this is the expression for the velocity when the particle is moving along a parabolic path. So let's check if we got the right answer. So we have 2k over L times cosine of theta over 2. 2k over L times cosine of theta over 2. Yeah. So this is correct. Now let's move on to the elliptical path. So we'll check out that our expression for velocity turns out to be given by this particular expression. Fine. We'll again start with the same formula for the velocity. So let's note that. Now for an elliptical path, we know that the value of the eccentricity, it has a range that lies somewhere between 0 and 1. So what we're going to do, we're going to do a little bit of manipulation here. So we can rewrite that expression within the parentheses as, so 1, so we'll write here 2 minus 1 plus epsilon squared plus 2 epsilon cosine of theta. So what we are going to do here, we are going to combine this 2 and this 2 epsilon cosine theta. So this is going to give us L squared divided by M squared times L squared. So we have 2 common, so this will be 1 plus epsilon times cosine theta. And we'll combine the second and the third term. So let's take negative as the common factor. So we have 1 minus epsilon squared. Fine. Now the reason why we have done this, because we know that we are, according to our definition, R is given by L divided by 1 plus epsilon cosine theta. So that means in place of 1 plus epsilon cosine theta, so we have L over R. So we can replace it here in place of 1 plus epsilon cosine theta. And also, we know that the value of A is given by L divided by 1 minus epsilon squared. So that means if we have 1 minus epsilon squared, so that will be simply L divided by the semi-major axis A. So let's substitute these values here. So we have L squared divided by M squared times L squared. So this will becomes 2 times L divided by R minus L divided by A. Fine. Now what we can do, so L is common to both the numerator, so we can pull out that L from the numerator. So this will come out here. So this goes away. So this will be simply 1 over a. And 1 L from the numerator and 1 from the denominator goes away. So that our expression for velocity now becomes L squared divided by m squared times L. So we have 2 over r minus 1 over a. Next, we need to substitute the value of little l. So that's the semi-lattice rectum. We will be substituting the value of L with L squared over mk, such that the expression for our velocity now becomes v squared equals to, we have L squared divided by m squared times L. So L will be L squared divided by m times k times 2 over r minus 1 over a. So we have the L squared cancelling out, 1m gets cancelled. So this will be equals to k over m multiplied to 2 over r minus 1 over a. And what we'll do, since we have to obtain expression for only velocity, not v squared, so we'll take the square root on both sides. So we have square root of k over m times 2 over r minus 1 over a. So let's check it out if we've got the right expression or not. So square root of k over m times 2 over r minus 1 over a. So yes. So this is what we are asked to show, and we have got exactly this particular expression.